So a dichotomy is a situation with only two possibilities. Unfortunately for us, there are not many true dichotomies in real life. For example, saying that something's either black or white is not a dichotomy at all, because if it's not black, it doesn't have to be white. It could be red or purple or green. All right. So most situations have more than two possibilities, but some situations have only two possibilities. And most of these situations happen in math. For example, either x equals 2 or x does not equal 2. There is a true dichotomy right there. All right. And so I'm going to demonstrate this reductio ad absurdum proof by proving theorem 6. All right, so let's prove theorem 6. We have just enough room down here on the bottom to do that. So we're going to have given triangle ABC with the base angles equal. All right, so I'm going to draw ABC down here. A, B, C. You can't see it yet, but let me move my stuff around on my desk here. There we go. All right. And angle B, I'm going to have given to be equal to angle C. Only I'm going to call angle C ACB for reasons that you will find out later. All right? So we have to prove that if these angles are equal, then AB equals AC, and it's an isosceles triangle. Okay, so the first thing I do is establish the dichotomy. And the dichotomy is going to be based on what I want to prove. See, so the dichotomy is this. Either AB equals AC or it doesn't. There are no other possibilities in the universe in this situation. If these two angles are equal, either these sides are equal or they're not. All right. And so what we're going to do is we're going to assume that they're not. And then we're going to show that that's impossible, as that if we assume that they're not equal, it's going to lead to a contradiction that is a logical contradiction of something we already know. So we're going to assume AB does not equal AC. All right. Now, if AB does not equal AC, that means one of them is bigger. It doesn't matter which one is bigger. We're just going to let AB be the bigger one. Let AB be bigger than AC. Well, what does Euclid do when he has one line bigger than another? Well, you know from theorem 3 that if one line is bigger than another, Euclid says we can cut off the longer one to make it equal to the shorter one. All right? And so that's exactly what we're going to do. We're going to cut off AB at, let's say, D, so that BD equals AC. All right? So what you have to do is take AC, which we're going to eventually prove is equal to AB, but we're just pretending for the sake of the proof that AB is actually bigger. Okay? And so we're going to pretend to cut it off, let's say right there. And so if AB and AC are not equal, then we're going to say AB is bigger, and we're going to cut it off and make it equal to AC. So now we know that AC and BD are equal to each other. All right? And of course, that makes this new point. And when Euclid makes a new point, oh, and by the way, we can do that because of theorem 3. Hooray. We used theorem 3. However, now we have this new point. And of course, when Euclid has a new point, he is going to connect it with another point. So we're going to draw DC. Now, DC actually cuts angle ACB into two angles, doesn't it? ACD and DCB. All right, that's why we had to call this ACB up here, because there can't be, there's 3 different angle C's. So if we had called this angle C, we would now be confused. Angle B is equal to which angle C? Well, it's the big angle C, ACB. All right. Now, after I draw DC, we have an interesting thing here, is that we now have 2 congruent triangles. Maybe you can't see them, but let me show them to you. I'm first going to say that BC is equal to itself. That's axiom 4. And by the way, drawing DC is postulate 1, as you know. All right. So now I'm going to say BC is equal to itself. Now I have side, angle, side for triangle DBC. This side, I have this side, and I have this angle. And then I also have the original triangle ACB, and I have AC is equal to DB. I have BC is equal to itself, and I have this angle ACB equal to this angle B over here. So these 2 triangles have to be congruent. DBC must be congruent to ACB by the SAS. And if the triangles are congruent, then we know that their areas are equal. And this is how you denote area in geometry language. You put the name of the triangle in brackets. So now we know this area is equal to this area, but that's absurd, because look at this triangle. If we say that the area of this clearly smaller triangle is equal to the area of this larger triangle that it's a part of, then what does that contradict? It contradicts the whole is greater than the part. So here we have the part of the triangle, and it's equal to the whole, which is absurd. That's the fun part of this proof, is that you get to say that something's absurd. And clearly it is. The part can't be equal to the whole, because that contradicts established axiom 5, that the whole has to be greater than the part. The whole can't be equal to the part. And so then we get to say, hence what we assumed back here, that AB is not equal to AC, must be false. And hence the only other possibility is that AB does equal AC, QED. Brilliant, huh? All right. That's theorem 6.